probably scary, wasn't it? Welcome to Honors Chapter 9 Test Hints, kind of wrapping things up as we're getting nearer and nearer the end of the year. This is a nice, short, sweet chapter, some basic concepts here. It's a short test, just 25 questions, and there are some short answers on this test. About, let's see, like the last 5 or 6 questions are short answer on this test. Very similar to what you'll be doing on the honors page for this chapter as well. And even the multiple choice have quite a few of math calculations and things involved in them. Okay, so we start off with the first couple questions that are just basic definitions. And the hint says, define composition and reaction stoichiometry. We were doing composition stoichiometry back when we were writing chemical formulas and looking at mass percentages in a chemical compound. So we would focus in on one compound, say this potassium chloride here, and we could use the atomic mass from the periodic table to determine what percent of the mass of that whole compound KCl is potassium and what percent is chlorine. And we would do that simply by dividing the atomic mass of potassium by the molar mass of the compound potassium chloride times 100, we get a percent. That's an example of how to do some composition stoichiometry. In this chapter, chapter 9, we moved on a little further to reaction stoichiometry. This is the recipe for a chemical reaction, and I'm going to be referring to this potassium chlorate decomposition reaction just as a convenient reaction to look at because it has some ratios that may not end up one-to-one. And in a reaction stoichiometry problem, we're comparing one substance to another. We could be comparing a couple of reactants to each other. We could compare a reactant to a product. We could compare a couple of products with each other, or a product back to a reactant. Doesn't matter what we start with or what we ended with in terms of where it is in the chemical equation. We're comparing the amounts of one substance to another based on this recipe, this chemical reaction recipe. Of course, you know we have the Brownie lab in this chapter where we're working with limiting reagents and we want to see what effect that has. It is delicious and interesting, depending on who's the baker. Okay, so the first couple questions, general kind of definition questions distinguishing between those two kinds of stoichiometry. Moving on to test hint number 3. What can be found out about a reaction when the mole ratios are known? Okay, so in this balanced equation, our mole ratios are 2 to 2 to 3. That's what the coefficients are telling us. They tell us the amounts of moles. And typically we're working with a large amount of substance compared to individual molecules or formula units. We know that that 2 to 2 to 3 ratio also applies to molecules and formula units, well, formula units in this case, molecules for oxygen. But we're never looking at one tiny little piece of stuff. We have to measure lots of them together. So mole is our best unit to coordinate. However, if we know that, and we know a starting mass of the substance, so we start with a particular mass, 5 grams or something, we can figure out the masses of the other substances involved. And that general format that I showed you is the mole tunnel, which is just a catchy little mnemonic to help you remember how to do these. Same thing as the train tracks that you've seen in videos on our Moodle page and examples that we've done in class and so on. But the key to all of those, of course, is the mole. So we're going to keep my couple examples of moles handy here when it comes to ratios. Test hint number 4 says how a mole ratio is determined for a given reaction. Okay, well, the mole ratio for a given reaction is essentially a constant, and we'd be in the simplest whole number ratio of moles. And we do that by balancing the equation by counting atoms. We're looking at how many atoms, say, of potassium go in and how many atoms of potassium come out. How many atoms of chlorine go in, how many atoms of chlorine come out, our oxygens, and so on. And based on the subscripts on the compounds here, we have to put in these particular coefficients to make sure that the law of conservation of atoms was followed, that we did have equal amounts of substances on the reactant and product side. Okay? So that goes back to simply balancing an equation. And again, we always want to reduce that down to the most basic ratio. So in this particular question, this is a very straightforward example of just looking at a mole ratio. Number 6 puts that in context with a specific question. Actually, number 5 and 6, I jumped ahead a little bit. How to identify a specific mole ratio for a specific reaction? Well, 2 questions, basically asking the same, well, they are asking the same thing, and I'm giving you 2 different equations. As I glance here, I see that they happen to be balanced equations as well, and it will ask you the moles of one thing to another. So how would that look in terms of our potassium chloride example? I might say, what is the mole ratio of oxygen to potassium chlorate in this decomposition reaction? Well, the number in front of oxygen is a 3, and the number in front of potassium chloride is a 2, so that's simply a 3-to-2 ratio. This question's as easy as that. Test it number 7. How to determine the number of moles of product in a given reaction. Okay, and number 8 is the same. So again, 2 more balanced equations will be given for 7 and 8. And this time we're adding one other layer of difficulty to this problem, which is still really easy. And I'm saying, well, what if we had 6 moles of oxygen? How many moles of potassium chlorate would we need to decompose in order to get 6 moles of oxygen? This is a basic proportion. This is like elementary school math. You could do this. If 3 is to 2, then 6 must be to, let's think about it, 4. Okay? Problems just like that, using the ratio in the balanced equation. Now, by the time you're watching these, we will have done a lot of other problems that are more difficult. We will be going through the whole mole tunnel. We'll be looking at that ratio as one of our steps in a mole tunnel problem. So you've done lots and lots and lots of this. It might throw you a little bit to go back and have a question that is that easy, but it really is a question that is that easy. Moving on to test hint number 9. How to solve a mole mass problem for a given reaction. 9 and 10 are the same. Moles to mass. So we're starting with a particular number of moles, say potassium chloride, and let's compare it to potassium chlorate. That's a 2-to-2 ratio, which means it's really a 1-to-1 ratio. If I put in 5 moles of potassium chloride, then I would also need 5 moles of potassium chlorate. But how many grams would that be? What would the mass of that 5 moles of potassium chlorate be? Well, you know how to convert from moles into mass. You simply multiply by the molar mass of the compound. So you'd have to add up your molar masses. I've jotted them down here just as an example. And we would multiply our number of moles by that. So that's the second kind of problem. We have mole-mole ratio, we have mole mass, we also have mass to mole, which is the same thing I just explained, but backwards. And then we have the full-blown mass-mass problem. So our next 2 examples